before I get started, how many people are mobile developers in the room? Okay, so what does that make the rest of you? Is it like server, backend people is the rest? Is there anything else that anyone wants to yell out? Okay, so this talk is about reactivity and reactive libraries. And I am a client developer. I work on Android apps. So most of the talk is framed from that perspective. However, there's nothing inherently unique to client development that isn't also true for server or really anywhere. And so the examples might be for Android, and I'll reference Android a lot, but I'll do my best to frame it from different perspectives. And then at the very end, actually talk about kind of future versions of Java, which aren't even relevant for Android. So my name's Jake Wharton. I work at a company called Square. And this talk is about reactivity in general, although I will be primarily focusing on RxJava, which is a Java implementation of a reactive library. And so the way I like to start enticing people about reactivity is with a fairly bold claim, which is that unless you can model the entire system that you're interacting with in a synchronous fashion, then adding something asynchronous to it is going to break down imperative programming. And this isn't break in the sense that it becomes not feasible or unfunctional. It's break in the sense that the complexity starts to scale in a nonlinear fashion. The more asynchrony that you add to your application, the complexity just compounds and becomes really exponential, and a lot of the burden of managing that state is pushed onto you. And so I'm going to illustrate a little example here to kind of prove this out. So if we have some hypothetical type that's managing users and has mutators that allow us to change properties of that object, if this is fully synchronous, we can interact with it in the obvious synchronous ways, and everything is really easy and works as we expect. The problem, however, comes when we introduce something asynchronous. So now these mutators, say, have to make a network call, or they have to write to a database. You can still do this synchronously, of course, but again, framing it from the client perspective, we wouldn't want to block interaction with an entire application just to make a network call to mutate some property. We want this to happen concurrently with other interactions in the system. And so what do we have to do in order to support this? Well, one thing we can do is nothing, right? We can just be optimistic and say, I'm going to make this action, I'm going to change this name or set this age, and I'm going to assume that it's just going to work. Obviously, this falls over fairly immediately because networks are broken, databases have concurrent write issues, maybe your change is superseded by one that had already happened from a different node, or potentially the write actually succeeds, but then the user has modified a property by talking to another server that wrote to the database, and now your local representation is stale. So nothing is always the wrong answer here. We can start to try being more reactive, I'll give a callback so that when I make these mutator calls, I can pass a lambda and be returned when the value has been updated, and only then will I print out the new user value. This, of course, works and is reactive, I guess, in some definition, but we lose the ability to message failure cases. We're only concerned about the success case, not what happens if it fails. So we could create a little bespoke listener that's specific to this type that now encapsulates all the potential responses, in this case just success or failure, and we can use that listener and message the person interacting with this system appropriately. And this sort of works, but again, we start to run into problems when there are multiple of these things happening. So what if I'm also setting the name and the age basically at the same time. These are now asynchronous calls, so both of these are going to start almost immediately. There's not 2 cases that we have to handle here. There's actually 4, right? There's the case where there's both succeed, the case where both fail, and then the 2 cases where one or the other succeeds and then the other one fails. And so by having 2 of these, we now have 4 cases, and if we were to add a third network call, that would turn into 8, et cetera. Additionally, if you want to start composing these things such that they're chained, where the result of one action turns into the other, you have the added, you still have the 4 cases, but of course there's the added complexity of composing them yourself. And so when you're usually doing stuff like this, it's in some greater context. And so for this case, this is an example in an Android activity, which is the sort of base primitive of how you show UI to the user. There's all kinds of additional concerns that come from this surrounding context. So in this example, we're interacting with the UI. Well, we have to make sure we don't interact with the UI after that UI is actually not being displayed to the user. So we have to remember to check that. We're also passing a callback to this function, which in Java actually is going to keep a reference to the enclosing class instance, the enclosing instance of the enclosing class. And so this, in the case of Android, is actually a memory leak. Until this network call comes back, either successful or failure, we've leaked the enclosing instance for anywhere from seconds to minutes. Anywhere there's UI, threading is a concern. So both on desktop applications and Android and iOS, there's a main thread through which you can interact. You can only interact with the UI. And so if these come back on, say, a background thread because it's a network call or database interaction, then we are the ones responsible for now handling threading. So all these things just start to compound. And I'm not even taking into account things like user input, disabling buttons, disabling input fields, et cetera. And so what's going on here in a different representation is that we have our code living inside the system, and it's interacting with these multiple asynchronous things. So we have the network where we make requests, we get back responses. We have the file system, which is potentially actually files or a local database that we're setting writes to or reading data from. We also have the user of our system, which is something you often don't think about, but which is an inherently asynchronous source, right? You send data to the user in the form of basically your UI, or in the case of a server, it would be like responses to requests. But then additional interactions with that system come asynchronously. You don't know when the user is going to click on that button. You don't know when the user is going to press back on their browser or send the next request to your backend. Those things, from a scaled out view, are inherently asynchronous. And so the UI of our system, whether it be in the Android case, just an activity, from the server case, it's kind of the client, that is also an inherently asynchronous source. And so all of these things are sort of happening concurrently. And it's our code that sits in the middle, which is what I showed more towards in the last example, which is dealing with all of those things and trying to make sure that the state of the world is in the right state. And it becomes complicated to wire these things up yourself. You have to explicitly state that when a network call comes back, that gets written to the file system. And you have to explicitly state that when some object is updated from the database, that gets piped into the UI. You're explicitly stating all of these dependencies and managing them yourself. And then there's, again, in the case of Android, there's the actual operating system that surrounds you. In the case of like server, this would be the instance of the JVM perhaps that you're running on, right? Like there's things that are happening in the JVM that you have to be inherently reactive to, such as memory pressure or the JVM actually shutting down, or not even JVM. I shouldn't assume Java, but your enclosing application instance is reacting to things from either the operating system or the instance itself. Let's go back to this statement. Mixing together this imperative code with sort of these bespoke reactive systems just winds up pushing a lot of complexity onto your code for managing when things are in flight, when these asynchronous actions are happening, how they're being coordinated, where the data is flowing to. It's all very explicitly and very imperatively detailed in the code that you write, and it becomes, the complexity just scales to a point that it can be really potentially impossible to understand all the different data flows and states that your application can be in. And so this is the point of writing code reactively, is that you're not getting rid of those explicit connections between these things. You're just, instead of managing it imperatively yourself, you're doing the work to hook the things up so that one just reacts to the other. So instead of all these arrows flowing through our code, what our code can do is actually be the one that hooks things together such that now the UI will automatically populate once something in the database changes. Now a database change or a network call is going to happen automatically when the user clicks a button or refreshes a page. Network requests that either are going out or coming in automatically take the data and write it to your data store. And then those indicators from your system, whether it be the app that you're running in on Android, the VM or process that you're running in on the server, those events just flow into the appropriate parts of your system and can be reacted to automatically. And so the code in the middle starts to disappear, and it's not that there's no code still on this slide, it's just that the code that we're writing is now the arrows and not the very imperative code that has to keep track of all the state and has to remember who is listening to what event sources. And so this is where we get to RxJava, which is the library one of the libraries on the JVM for writing reactive code. I should say one of the libraries for Java, since it works both on the JVM and Android. And RxJava is mostly three things. So you have a set of types which represent sources of data, places that data can be obtained. And this is going to be things like the network, the database, the file system, et cetera. And then you have types which are for listening to that data. What use is a source of data if you cannot in some way listen to it and see the new values that are being emitted from it? And then there are these primitives, these methods, which allow you to modify and compose the data in some way. So combining and splitting sources, transforming the data from foo to bar, et cetera. These are the three main areas of the library. The three main things you need to understand in order to use it effectively. The first two are very related, so we're going to look at those together. So sources in RxJava are where data originates, and typically they do something when you start listening to them. And so an example would be representing a network request for, say, google.com. And this source is not going, when you create this source, it's not going to make the network request right away and then you start listening and get the response. It's going to be a lazy thing that only when you start listening does it actually send the request, and then when the response comes, it notifies you. Another example would be like a database query. You create the database query as an RxJava source, and it doesn't start executing. It doesn't actually talk to the database. It's only when you start listening to that source does it actually reach out, execute the query, and then deliver results to you. These can be either synchronous or asynchronous. So, file system reads, database accesses, even network calls. You can model synchronously that are going to, block a thread and actually wait, or they can be asynchronous in the case of, say, the user clicking on a button, or if you have an asynchronous way of talking to the file system, network, et cetera, you can model those things in that way. These can represent either a single item as its response, which is the case of like a network request, or multiple items, which is the case of a database query returning rows in the database, or like the button click example where the user can click on the button multiple times. They also can represent empty sources, which are it's work that is done that that doesn't really have a result. Example of this would be like writing to a database. If you're inserting a new row, assuming you don't care about like the ID or whatever that's inserted, you only really care about when it's done, or if it errored, you don't really care about the item itself. These sources have terminal events, and so after they send you some data, there's two terminal events. They either error, which means no other, it's the work didn't complete successfully, it completed exceptionally, and there will be no additional notifications after that, or they just succeed, which is also an indication that no additional events will follow that. But they also don't have to terminate at all, so they could be infinite sources of data. Again, the button click example is a really good one here, where your UI may disappear, and so you stop listening to button clicks. But as long as you're subscribed to this button click source, it's really infinite. It's never going to terminate. And basically all of this is just the observer pattern. But what it is the observer pattern kind of on steroids. It's all these primitives in RxJava are built to make the observer pattern work a lot more for you instead of you having to do a lot of the work for the observer pattern yourself. So there's two types. There's two main types which represent sources of data. One is called observable and the other is called flowable. And they both model the same shape of data. And by shape, I mean kind of how emissions happen and how they potentially complete. And so both of these represent anywhere from 0 to infinite or a certain number of items. And then they will either terminate with success, or they will terminate with an error, or again, potentially not terminate at all. The reason we have two different types is that one supports something called back pressure and one does not. And so observable, the one on the top, does not support back pressure, and flowable does support back pressure. And so we'll see why this is interesting and useful. So the RxJava that I'm talking about, which I didn't mention earlier, is actually RxJava 2. And so in RxJava 1, this distinction did not exist. And back pressure is also in RxJava 1, and it's sort of the way that you can control how fast data is being pushed into your listeners. You can say, I only have a finite set of resources. My queue is only so big. I only have so many CPUs, et cetera. So you're able to slow down the emission of data so that you're always able to successfully process it. This is, an extremely important concept, especially for our servers and scalability. The problem and the reason we have two types here is that RxJava 1, back pressure was added fairly late in the design process. And so it was able to be retrofitted in what they had already built, and it actually came out really well. But the problem is that every source that you created acted like it had back pressure, but some of them didn't actually respect it. So you would have something like, actually we'll look at an example next. But the key here is that you can't expose back pressure and then when someone tries to slow you down, be like, well, I can't do anything. Like, you have to take everything I'm giving you. You have to really design for back pressure, and if you have to design for it, that means potentially some sources aren't going to implement it, either because they didn't design for it or they just actually can't be slowed down. It means that you have no way of knowing. As you're composing and combining these things, you have no way of knowing which sources can be slowed down or not. So a simple example. Again, going back to, in this case, Android, if you're interacting with a device and you're taking your finger and painting across the screen, what this is going to do is send what's called motion events. And if you model this in RxJava, you'll get a stream of motion events. And so for every change that the display can detect with your finger moving, it'll send an event. This is an example of something that just can't be slowed down. There's no way for you to apply back pressure up through the physical display and slow the user's finger down. Tell them, oh wait, you got to stop while I render these points that you just sent in, and then now you can continue. There's no way to physically communicate that back into the user's finger. Contrast that with, say, a database, where you're writing a query to select a bunch of rows. You only have processing space for a certain amount. So you say, I only need a few. And then, OK, time's gone by, I've processed, I have a few more. OK, now give me a few more. In RxJava 1, if you try and apply back pressure to both of these sources, it's going to work on the one on the right, the database. And on the left, you actually get it'll throw an exception. It'll send an exception down the stream, so it's going to terminate with an error. This is the reason that the distinction between flowable and observable exists in RxJava 2, is that now this concept has been elevated into the type system. So by looking at the type, you can know whether or not the source is going to support back pressure. And actually, because it's in the type system, we can now use the compiler to enforce the fact that you can never apply back pressure to an observable. The way this manifests itself, so these are the two listener interfaces that you can use to listen to a source, and they're almost exactly the same. We have a callback where we get the data that we're interested in. So when we're listening to a source, this is what's going to be called over and over for every item, or potentially once if there's only a single item. We have the terminal events, the complete case where it was successful, the error case where there was something exceptional happened. And then we have this last callback, on subscribe. On subscribe is basically it's the first callback that happens when you start listening. It's the source telling you that you are now subscribed to it, and it gives you an argument, and that argument is kind of a handle to your subscription. For observable, we get a disposable, and a disposable is a single method interface that allows you to unhook from that source whenever you want to stop listening. And so we have a single method called dispose that just disposes it disposes your subscription, your intent to be listening to items, so that you receive no items after you call that method. But for flowable, we get a subscription, which actually has two methods. So here you have cancel instead of dispose, and I'll talk about that in a second, why those are different. But we have an additional method called request. And so this is the mechanism through which back pressure happens. You request a certain amount of items when you get this on-subscribe callback. You can request long max value, which basically says, open the floodgates, like send me as fast as you can. Or you can do much more granular requests, which is like, all right, give me 128 items. And then once those start processing, you can sort of get a feel for the source, if you will, and request more and more over time as you're aware that you have the resources to process. So to put this into a little chart, which we'll add to in a bit, these are the two types which represent the same shape of data. It's the same type of sources that you want to expose, the only difference being that one allows you to slow it down, and the other is basically a unbounded source. So this brings me to something called reactive streams. This is just about 2 years old, or actually maybe a little more than 2 years old now. Reactive Streams is an initiative to create these shared APIs that all reactive libraries can expose, such that if you have an observable from one and you have a type from a completely different library, that they adhere to the same contract and you can combine and compose them as if they were from the same library. It's effectively the list interface for reactive sources. So given array list, linked list, you don't really have to care about the implementations. You can always use them as a list. This is the reactive version of that. And it's 4 types. So publisher, which is the source of data. In this case, this takes a subscriber. Subscriber is that type that we already looked at, that Flowable was using, which is the listener, or the observer, if you will. Then we have that subscription, which is the resource, the sort of handle on the subscription that you can use to unsubscribe. And then finally, there's a type called processor, which is both a subscriber and a publisher, which is kind of like almost a pipe, like something that you can dump data in and also listen to from somewhere else. The top three are the important ones here. And so going back to the chart, the left is actually the reactive streams types. And then the one on the right, the back pressure free one, is observable, and that's just an RxJava specific source. So if you have an observable and you want to pass it to someone that only knows about reactive streams types, you have to first convert it to a flowable because it's the only one that implements that specification. Okay, so going back to our hypothetical user manager here, what we were doing before is we were pulling out the user anytime we made a change to it and then rendering it. And so what we want to do here is flip that model where we're no longer imperatively pulling it out when we think we need to display a new change. Instead, we want to reactively receive new updates to the user whenever the implementation wants to send us new ones, and then we just do the right thing with that. We display it to the user, we propagate it to the database, we send it over the network. We no longer have our code that's consuming this interface no longer has to make decisions about when to pull the user, when's the correct time to look at it. Instead, it just has to react whenever the implementation deems that the user has changed. Okay, so we talked about observable and flowable, which are sort of the big heavyweight types. There's a few specializations of sources that I want to look at. And similar to why we have the distinction of observable and flowable, these exist to encode subsets of sources of data also into the type system. The first one is called a single, and I bet you can guess what it does. This is a source of data that only has a single item. So it either completes with a single item or it errors with an exception. And it doesn't support back pressure. This is essentially the reactive version of just a scalar. So you call a method, you get a return value. This is basically what a single is, except it's now a reactive version. So you subscribe to a single, you get a single value back. Completable is the next one, and this actually has no items whatsoever. It either completes successfully with no item, or it errors with an exception, also no back pressure. And this is like a reactive runnable. It's an operation that you want to happen, and you just want to know if it succeeds or if it throws an exception. Another way of potentially thinking about it would be it's like a reactive version of a method that returns void or doesn't have a return value. You just want to run the contents of that and know whether once it's complete or if it had thrown an exception. This is the reactive version of that. And then the last one is called a maybe, and it is sort of a combination of both, where it may have an item, or it may complete without an item, or it's going to error with an exception. This is basically the reactive version of an optional scalar. So you could think of it as like a single of optional, except now it's encoded into the type system instead of just encoded into a generic of single. So these are our three specializations. There are no reactive streams versions of these types. They don't implement the publisher interface. So again, if you need to expose these to across those boundaries, you have to first convert it into a flowable. And so for our example, when the set name and set age mutators became asynchronous, these run, and then we need to know whether they complete or error, which means we want them to return completable. Okay, so I've talked about what these sources exist for. We haven't really looked at how you create them. There's factory methods that you would expect on them to create them from simple pieces of data. So if you have literals, or you just have variables that you want to wrap in these types, there are static factory methods. If you have iterable sources or arrays, again, factory methods. The interesting ones, however, are when you want to adapt something else in your system. So if you have something synchronous, like a method call that returns a value, the easiest way would be this from callable static factory method, which will execute the callable every time someone subscribes. So by subscribing to the observable that's returned from this method, it will in turn execute the callable, which will in turn call the getName function. The value that it returns will be then propagated to the listener. What's nice about this is that callable allows you to throw any exception. And so you can do things like network requests in here or other blocking synchronous interactions, and any exception that's thrown from the callable will be propagated to the error handling of the listener, to the observable of the subscriber. From callable exists on all 5 types. Both maybe and completable, the 2 types which are allowed to complete without an item, have 2 additional ones called from action and from runnable. Again, like I said, the reactive version of these methods that don't return a value. And the reason that there's both of these is that runnable, unlike callable, doesn't let you throw exceptions, or checked exceptions, I should say. And so the action interface allows you to do that. So if you need to call a void method that throws a checked exception, you'll want to use action. And again, writing to a database, writing to a file, those are the cases where you would want to use either, well, in both those cases, probably the completable version, but if you, for whatever reason, need to return a maybe, you could as well. All right, but the most interesting static factory method is aptly called create, and it's also the most powerful. This basically allows you to adapt any style of API into the reactive world of RxJava. It takes in a Lambda type, and that type has just a single argument, a single parameter, I should say, and this is basically the downstream listener. So when you subscribe to this type, this subscribe method will be called, and you get a wrapper around the person that's listening to you, and then you can just shove data into them. So in this case, I'm doing it synchronously, where I'm just sending a value and then completing the stream. You also could send multiple types here, or no types at all. You could call on error. If you have asynchronous sources, so you want to wrap something that already has a listener, this is how you would do it. So inside that function, you would call your asynchronous thing, and then in its callbacks, you can then propagate that to either on next, on error, or on complete. And the reason that you would want to do something like this is that the whole point of modeling things in RxJava's types is that it normalizes them all under the same interface. It allows you to treat both a database write, a database query, a network request, interactions with the user interface, all as the same type. And then soon we're going to see how they kind of can get composed together. But you normalize them so that every interaction starts to become the same. Another really awesome feature of using this create factory is that you can set a cancellation callback on that emitter, that argument that's passed in. And this is a Lambda that's going to run whenever the listener unsubscribes. So in this case, I'm making a synchronous HTTP request. And if I subscribe to that, wait 2 seconds, and the response doesn't come in, maybe the user moved on in the UI, or I just don't want to wait. I unsubscribe from that, and instead of just allowing that work to continue, say for 10 seconds or however long, we can actually have this function run and then cancel the call and free up that resource. Again, going back to mobile, this is how you would adapt things from Android's UI callbacks. You can turn, Android basically has tons of widgets, same I guess for desktop Java, if anyone's doing desktop Java. You just have a bunch of bespoke listeners, callbacks for each of these widgets that you can't reuse. You have to use the button click listener. You have to use the list item selection listener. You have to use all these different ones. Instead, you can normalize them so they all appear as the same fundamental type. And so code that you write against that type can be reused for lists, buttons, etc. And in this case, we're unregistering that listener automatically when you stop listening to the source. This create function available on all 5 types. And so that primarily gives you ways to create these. I didn't also mention that a lot of libraries will simply provide you with observables or flowables already. So if you use a networking client or a database client, a lot of times they will actually just give you an observable, and so you don't become concerned about how to create them. You really just become concerned about how to listen and how to compose. So going back to how do we actually listen to these things, we looked at these interfaces already, and we looked at the difference between the subscribe types. And what's interesting is we're given this handle to the subscription, which is the mechanism we can use to unsubscribe. But if we're implementing this, especially if you're familiar with RxJava 1, this fourth callback is something new. And so what you want to do is not lose that disposable, because otherwise you're essentially at the mercy of the source and you can never unsubscribe from it. But it's sort of annoying that you have to manage this within the callbacks instead of having a reference to the subscription when you actually do the subscribe call. And the reason for this is not only because of those reactive streams interfaces, but because it actually allows the internal architecture of RxJava to be a lot more efficient. However, at the leaf nodes of subscribing, when you're actually doing the subscribing, there's some convenience ways which don't force this fourth callback on you. So there's a type called disposable observer. And what this is going to do is automatically keep track of that disposable for you, so you don't have to worry about putting it in a field, or in this case, there'd be no way of getting it into like a local variable of the enclosing method. But if we're just calling it like this, we still don't have that reference. So you can either just keep track of the observable as your disposable object, and then whenever you're done, you can call dispose on the observable, and then it'll work its way into the disposable that was handed to it, and it'll work its way up the stream and eventually stop the source. There's actually a convenience method, however, called subscribe with, which is probably the thing you're going to want to use, and this is just ends up returning a disposable to you directly. If you've done RxJava 1, this is how you always subscribed, and so this will feel very familiar. And it's basically the easiest way of getting back the disposable as a local variable from actually calling the subscribe, which is a little more intuitive, a little more how you think about getting a resource handle into the thing you're subscribing to. If you're subscribing to multiple sources at the same time, you can manage those using something called a composite disposable. Basically, is kind of just a list of disposables. Super important on Android because we see a lot UIs subscribing to a lot of sources, and then when the UI is disappearing, you want to just unsubscribe from all of them at once. These disposable variants of the observers exist for all 4 of the non-reactive streams types. And then for the reactive streams flowable, there is a disposable version of its subscriber. And again, all of these end up returning a disposable reference to you that you can then keep track of yourself, put in a collection, etc. It's the same as, the right way to think about this is like any other stream or any other resource. When you open a file, when you connect to a database, when you make a network call, you don't just let that fall out of scope and hope that garbage collector saves you or reference counting saves you or whatever. You tend to manage those resources yourself so that you can free them at the soonest possible time, I should say. And that's exactly what these disposable references are. So they should be treated accordingly. Okay, so we looked at the types. Now let's look at the ways that we take these sources and combine and compose them to make RxJava, to make interactions with these really powerful. So the main idea here is that we take the data that's flowing through these streams and manipulate them in some way, change them, strings to uppercase, take data right into the file system, split, combine. Threading, we can control threading using operators, so very declaratively moving from worker pool A to worker pool B, from background thread to main thread, from request thread to background worker. Again, manipulating emissions, which I kind of already covered. So the way to think about this is very similar to what you would do with normal data. So given a string, I want to turn that into an uppercase version of it, I would call a method on that string, and it would return a new instance of the string. You're applying an operation to the string to get a new one. In the reactive world, it's the same concept. Given an observable, which emits strings, we can apply an operation to every item and get back a new observable that will have the operator applied to it. And for every item, apply the operation that we put inside, in this case, map. And so map becomes the way that we take single items, manipulate them in some way, and produce a single item. Another example would be taking a string and turning it into multiple items. So we split a string on spaces, we get back, in this case 2, but we get back an array. And so in the reactive world, you would have an observable representing a string, and then you could apply the split operation in a map, and you're going to get back an observable of a single item, in this case, of arrays, and that array has 2 elements inside of it. And so this is this may be what you want, but in this case, I'd like to have the individual pieces be individual items in the stream. And so if I have an array, well, earlier we saw that you can create an observable from an array. So maybe I will call observable from array and return that. Well, the problem is now that I have an observable of string. And so you would have to, it would emit a single observable. You would subscribe to words, and then your on next callback would get an observable, which you would have to subscribe to in order to get 2 elements out of, which sounds terrible. So what we want to do is take the inner observable that's being emitted and sort of flatten it into the original stream. And funny enough, the method is called flatMap because that's exactly what it's doing. It's taking the source of data that you're returning. This function, this lambda is returning a new source of data, which in this case has 2 elements, and it's taking the items that emit from that inner observable and flattening them back into the original stream. So now if we were to subscribe to words, we would get, in this case, 2 strings out. We get hello, comma, and then world. So flatMap becomes the operator here. Moving on to threading. In the original example where I moved it into the context of Android, our callback came on a background thread. We had to move it to the main thread. In the Rx world, we can do that a lot more declaratively. So it's actually just a single operator, single line, which basically says, take the items coming from, in this case, the user, and I want you to observe its emissions on the main thread. So the person who subscribes to main thread user will observe items on the main thread, even though the ones from higher up in the stream are being emitted on a background thread. Another example, making a synchronous network request. So I'm blocking this thread, making a network request, getting a response. I know I can wrap this in from callable. Synchronous returns a result. That result ends up inside the stream. But if I subscribe to this, I said very early on that work starts when you subscribe. So I'm going to subscribe to this method. I'm going to subscribe to this observable. This observable is going to start doing the work on the thread that I subscribed on. And so what we need to do is change the thread on which the work is happening so that we don't block the person who's subscribing. So what I want to do is subscribe on a different thread. In this case, schedulers IO is a thread pool, which doesn't really have anything special about it, but because it's named IO, you're supposed to batch IO operations on it. And so I'm saying that when I subscribe to this background response observable, I want it to subscribe to the actual work on the IO scheduler, on the IO thread pool. And what's nice about this is, in this case, I'm trying to be very clear, and so I'm storing all of these in, individual local variables after every operator is applied. But I can just be chaining these, so I can create the callable, and then I can apply the subscribe on, which is going to return a new instance of observable. I can apply observe on, which is going to return a new instance of an observable. I can take the response, I can map it into a string, except this brings up probably one of the most important points of RxJava, which is that order actually really, really matters here. This isn't a builder. This is composing, it's creating essentially a sequence of things that happen in a particular order. And so in this case, having the map operation occur after we've already moved to the main thread, I'm now interacting with a network on the main thread, which on Android is not allowed at all, and so your app is going to crash. But if I reverse the order of those two operations, if I do the read of the response into the string before the data moves to the main thread, it's going to happen, in this case, still on the background thread. And then similarly, like if I want to split the string again and do my little flattening operation, I can also put that in this stream. And so you can very declaratively build up a series of operations applied to every item of data flowing through this stream, and then also very declaratively control the threads on which not only the original work inside, in this case, the source, but also the work that's happening in each of the operators downstream of the source, so inside the map, inside the flat map. You can very declaratively control all of those things. So, I talked about the specialized sources, the single, completable, and maybe. And I want to show where they actually come up in the context of operators. So, given an observable that returns numbers, you can call an operator on it. Maybe first. And first is going to return you a new source that only emits the first item from the original stream. And so if you used RxJava 1, what you would get is an observable that only has a single item and then immediately completes after that single item. But this is kind of weird, right? If you have a list and you call get0, on that list, you don't get back a list which has a single item inside of it, right? You get back that item. You get back only the item because you're requesting a single item. And so what we want is that when I call first on an observable, I get back a type that actually represents a single type. And so this is where you start to see those source specializations come in, is that some of the operators which narrow the scope of a stream return that narrowed type. And so in the type system, you can now know that this operator returns a single item, and so anything that needs to consume it will just see it as a single item, knows that it's only going to get a single item. If you call get index 0 on an empty list, you get a no such element exception thrown. And it's the same thing here. Single can represent either an item or an error. And so you call first and then subscribe to that stream. If the stream is empty, that single is going to terminate with an error, no such element exception. There's other operators which allow you to work around things like this. So you can call first element instead, which is actually going to return you a maybe. And a maybe can either have an item or it can be successful but empty. And so given an empty source upstream, subscribing to the maybe returned from first element will just complete with no data. For completable, there's very few operators that return it. I actually think this is the only one. If you just want to ignore the data flowing from a stream, you get back a completable, and that completable will wait to emit anything until the original source completes. These also exist on Flowable. So Flowable has all the same, almost all of the same operators, and they all return the specialized types, which is important because that means they don't have back pressure. So applying something like only getting the first element from a flowable means you lose the ability to slow down the source. But that kind of makes sense, right? I mean, you're only getting one element, so does it really matter that you can slow it down? No. This is sort of a chart that shows a good subsection. In the upper right-hand corner, you see the narrowing operators. So starting on the left, pick a type, and then go and, if I have a observable and I call element at, which is the equivalent of like list.get. So I call element at 2, that returns me a single because I'm asking just for a single element. And then the bottom left, there are widening operators. These exist to take a type of one shape and turn it into a more representative type of another shape. So if you need to take a single and pass it to something that only knows about reactive streams types, you would call toFlowable and get back a flowable that is only going to emit one value, but now that someone that only knows about those common interfaces can subscribe to. All right, so going back to our user manager, I showed how once we learned about the sources, how those methods should return an observable and how they should return a completable because they're now, we now want to be able to react to them. Now that we know about operators, we can actually start using them. So getting the user observable, I want to, again in the case of Android, observe all the items that are emitted every time the user changes on the main thread. And then I want to take those users and push them into the user interface. So anytime, say the database with our user updates, a new item gets pushed into the callback. For observe on, that observe on operator moves that callback to the main thread and then calls the our callback, which then takes the, renders it to a string and then puts that in some text box. And then because this is a resource, we're subscribed to a query on the database, which is going to do work. We want to manage and track that connection such that if our UI ever disappears, we can then unsubscribe and have that work no longer run. And then similarly, if we are mutating, making network requests, we want that to happen on a background thread pool. We want to take the result of that network operation, observe it back on our main thread, and then we can re-enable the UI, assuming the user hits send or something. And again, this is a resource. It's a network request that's being made, and in case the application disappears out from under us, we want to free that resource so that it doesn't leak the enclosing object. Okay, so I want to talk a little bit, really quickly, about Java 9. Java 9 has a JEP, which is actually complete, called More Concurrency Updates, JEP 266. And this is what it has to say that it's adding to Java. Interfaces which support reactive streams publish subscribe framework nested in a new class called Flow. These very small interfaces correspond to those defined with broad participation and support of interoperability across a number of async systems for the JVM. And if we pull up the Java doc or we go look at the source for Java 9 and download early access and hook it up in our IDE, we look at the Flow class, it looks really familiar, right? This is basically the exact same thing as the reactive stream specification that I showed you earlier. It's 4 types. The only reason the Flow class exists is just to collect them all in one place. It's exactly the same semantics as reactive streams. So this will effectively once Java 9 is not only released but adopted, will effectively supersede the reactive stream specification and become the new interoperability layer between these libraries. So in this example, in this presentation, I talked about RxJava 2, which is reactive streams compliant for the flowable type. There's another library called Project Reactor, which is used in Spring, the new version of Spring 4 or 5, whatever the new one is, as its native reactive type. And it also is a reactive streams implementation. And so in the future, what we'll likely see is a RxJava version 3 and a Project Reactor version 4, which instead of sharing the reactive stream specification as its common interfaces, will share flow.publisher, flow.subscriber, and flow.subscription as the common APIs. And so you can take a type returned from some future version of Spring with a future version Project Reactor 4 and use it with your RxJava 3 library that's coming from RxNetty or something. And so it's going to take a while for this to disseminate and get used. But the other nice thing is because the semantics of this interface are exactly the same as reactive streams, if you have RxJava 2 or Project Reactor 3, which implements reactive streams, you can write a very trivial adapter that convert it into these flow types, and it will have the same behavior. So this is just wetting your palate for writing reactively. I was at Devox very recently, and if you are a client developer, I gave a talk about how to manage state with RxJava, which you can feel free to check out. And other than that, that's all I have. So hopefully this encourages you to write code reactively, because it allows you to take the imperative state management code that you're writing, interacting with these both synchronous and asynchronous sources, lift them into a common interface that you can then combine, compose, and subscribe to in a normalized and consistent way. So thank you all for coming and listening, and that's all I got. We have about 2 minutes, 3 minutes for questions if anyone has. Yes, okay. Wait for the recording.
If you're writing a REST backend for this Android, is there some kind of server-side technology that would let you take requests as reactive objects?
Yeah, so the question is, if you're writing a backend for something that's reactive on the front end, is there a way to kind of translate like back pressure and stuff across that network boundary, or
even just write your backend reactively rather than having an HTTP
Sure.
server?
Yeah, so from the backend perspective, way that you would think about it is that requests coming into your system are a stream of requests coming in, and then you're either filtering, mapping, and then fanning out to databases, other services, combining those back into another observable, which you then return as an observable of responses. And then the application container that you're within, RxNetty is an example of this. If you look at RxNetty, this is basically what it implements. You have an observable of requests coming in, an observable of responses going out, and then you just write that middle layer, and it takes care of actually hooking up to the socket and parsing HTTP, turning into the types, and it takes care of your responses going out and making sure they go to the right connection and get written out. And so you can write both the client and the server. It's just the opposite. From the client perspective, we're making requests and observing the responses coming back. From the server perspective, you're subscribing to requests coming in and returning asynchronous results that are then written to the client. So yeah, the Spring, I don't know what you use, but RxNetty is the one that I've used. And then the new version of Spring that just came out, 4 or 5, whatever it is, builds in Project Reactor, which is another reactive library for Java. And so it has that baked in, and they have tons of samples and stuff you can look at. Any other? Okay, cool. We're out of time anyway, so thank you all again.